Hmm. Hello everyone, my name is Sarith and my seminar today would be about the spherical evolution of cosmic voids, dark energy, and simulations. It's about cosmology and cosmological simulations. Most of you may not be familiar with it. I'll try to cover the basics as much as I can and hope you enjoy it. Okay. I'll go through the motivation of this talk in the spherical evolution model and how dark energy affects the evolution of cosmic voids and compare the profile with simulations. Okay, firstly, voids are the underdense regions of the universe. So there's this dense region like clusters, stars, like that there are like a lot of matter around it, but there are also the underdense region that mostly is empty space and it's large. It's about like hundreds of megaparsec and is sensitive to like theoretical prediction, something like dark energy, modified gravity, because there's less matter, so less gravitational interaction, thus less nonlinearity. So it's a cleaner environment to work on. And the goal of this talk to explain like how we use like spherical model for explaining the void, the evolution of the voids, and compare it to simulations. This talk would be based on the paper from Demchenko et al. 2016. Yes. So, as I said, voids are the underdense region of the universe. We define the density contrast. So it's like the difference between the density and the background density, which is the average density, rho bar. So the ratio would be less than one for voids because it's less dense. And so the density contrast is the ratio of difference and the average. And the voids are often quasi-spherical. That means it's not perfectly spherical, but it could be approximated to be. And we have another parameter called peculiar velocity. We Most of you might know already that the universe is expanding. So our velocity would have the component that expands with the universe, and that is called Hubble flow. So uh, that component is this one, uh, h or Hubble parameter times the radius is the velocity of the expansion. So we could just subtract it and we will get velocity aside from that called peculiar velocity. And more over, universe could form a cosmic web, which is the web of structures. We have clusters. We have clusters together. It could form filaments, and if it's like cylindrical, and it could form walls if there are like 2D sheets, and also voids for underdense region. So as matter falls towards like dense region because of higher gravity, matter we could look at it this way that matter evacuated away from the void because void is underdense and evacuate to the edges of the void. That's another way to look at it. Okay, so the spherical model would treat void as a spherical shells and is evolving under gravity and expansion. And matter inside the shell determines its acceleration. It's useful because it's easier to solve for the equation because of the symmetry of the spherical shape. And we also assume that shells do not cross here. This one I'll explain later what it means, but is the point where spherical model fails to explain. Okay, so it's kind of like this. We approximate it. And the scale factor, scale factor is the variable to determine the expansion of the universe quantitatively. So when the universe expands, uh, the scale on the ruler also expands. That scale on the ruler stays fixed. It is this one, whole moving distance. So what is actually expanding? We include it in another parameter called scale factor. So scale factor depends on time and the proper distance. The real distance is scale factor times co-moving distance. And universe expands, so it is defined that scale factor equals to 1 today, so it's less than 1 in the past and more than 1 in the future because it would be larger in the future and smaller in the past. And universe is homogeneous and isotropic. We could on large scale, and we could determine the expansion by explain the expansion by the scale factor. By for example, the expansion rate, we could use Hubble parameter, which is defined as the rate of change of scale factor over its magnitude. So the unit is only 1 over time. So it's the rate of expansion. And it could be explained by Friedmann equations. Friedmann equations come from Einstein equation, and we put every uh components inside, and we have left with 2 or 3 equations. So the first one is energy equation. So basically, expansion rate depends on energy. Rho is energy density and K is curvature. We do not consider curvature here, so don't need to worry about it. And the second one is acceleration equation. Also depends on density. And another one is total pressure repeat could affect the acceleration equation. More energy, then more gravity, then the less acceleration, more deceleration, harder to move around, accelerate. Okay, the standard model for cosmology is lambda CDM model that the cosmologist has used mainly. Lambda CDM is composed mainly of components in matter, radiation, and dark energy. Matter is what we are, baryonic matter, and the cold dark matter. So it's approximated to be to have very low velocity or non-relativistic. So we don't need to consider pressure or the equation to each other because only the energy density, rest mass energy, mc squared is very high already. comparing to this. And as the mass is conserved, so the density dilutes with volume because mass is conserved. And the radiation has like positive pressure, and then the velocity is like okay comparable to like the pressure is comparable to the energy density in this case, and it dilutes faster as the A fourth. And dark energy is assumed for simplicity to have constant energy density, and it has negative pressure because as we see from this equation, the second equation, uh, if we have negative pressure, then the acceleration could be positive. That means dark energy negative pressure acts as repulsive effect or like cosmic expansion. And when lambda equals zero, uh, that is the Einstein de Sitter universe or Einstein de Sitter model that we'll also talk about in this presentation. So the radius of the shell of the void also follows Friedman equation, acceleration equation. And we consider like no radiation, no dark energy. So it's just matter. And matter energy density is just like mc squared over volume. And we have C equals 1. So uh yeah, it's just m over like volume. And we have classical Newtonian gravity here. Acceleration is minus gm over r squared. And they have like analytical solution, like parametric solutions. That, so there are two types of solutions, two criteria of the solutions that depends on parameter theta. So the first one is for overdensity or like clusters, halos that expands and then collapse again. uh, so you could see that the radius r depends on cosine of theta, so it's kind of oscillating, so it collapses again. While the underdensity, or for void in this case, it would depend on hyperbolic cosine, so it keeps expanding and expanding because it's the exponential term. Okay, and uh, as the void expands, it could collapse with matter or cross with matter, causing the phenomenon called pileup. So this is because density of the void is less than the background, thus having larger acceleration. So void has larger acceleration, it expands faster than the background, then there's like pileup of matter. That could be, and this could be like the point where spherical model could not be used anymore. I'll explain it more later. Okay, back to the evolution of the density contrast a little bit. So we define the density contrast as this one, the difference of the density and ratio of it. So since density of matter decays with a cube, that's also the case with 1 plus contrast. So we could solve for the evolution of AET or scale factor, and then solve again then for the uh, contrast. Okay, let's look at the real result. As the void expands, I explained it already that the pile of matter at the edge could be happening. So this could cause the density contrast to increase because matter like pile up with each other, void expands too fast. And then like ideally we do not have the algorithm or method to like dilute this or resolve this. So it could just pile up infinitely. And that could form a thing, infinite, like infinity, and that is called caustic. So in reality, uh, the the void age could remain finite by the non-sphericity, velocity dispersion, and stuff. That's when a simple spherical model breaks down. You could see that it starts from the most left side of the graph. Then it evolves, piling up, and goes very high. Okay, so the the thing before is the Einstein de Sitter model. Now it's lambda CDM. Why do we need lambda CDM? Why do we need non-zero lambda or dark energy? Because observations tell us so. That the universe is undergoing accelerated expansion. So, for example, from type 1a supernova, so allow us to measure the distance of like supernovae at high redshifts, and is fainter than expected in the decelerating universe or like only matter universe, or like with radiation and stuff. So, thus implying that expansion is happening. And by expansion, so there's no term at all that could lead to expansion because everything leads to like okay more and more negative a double dot, right, from the Friedman equation. So there should be this term called dark energy that has negative pressure to produce repulsive effect. And as like famously seen, so dark energy about 70% of the energy of the total energy of the universe, and dark matter and like baryonic matter. So we need to consider that. Really, really need to. And okay, so how does the evolution equation changes? So by using Einstein equation, in conclusion, there would be like another term plus like lambda c squared over 3 in the acceleration equation. So we have including like Newtonian effect and Newtonian gravity like we used before. So it's gm over r squared for the second term, the first term on the right side, and then lambda c squared r over 3. And we define it using omega lambda. I rearrange terms a little bit, and we have omega lambda is naught squared r. Okay, so the equation is this one, the evolution equation. So the last term acts as a repulsive force because it's positive, counteracting gravity. That means the gravity does not affect as much as in Einstein-de Sitter model. So for the same initial density contrast, uh, the universe in lambda CDM expands faster. It develops weaker density contrast over time because it's harder to collapse or to to gravitate to each other as we are expanding away from each other. And thus, since we are expanding away from each other, the shell crossing could come later. That means dark energy smooths out structure formation, slows the growth of like overdense, underdense. So let's look at how the result goes. So as omega lambda as acts as repulsive acceleration, it smooths out, the growth is slower, that comes this result. This is the result from the model from Demchenko et al. Uh, the dashed line is from Einstein de Sitter, and lambda CDM is in solid line, so it's clearly seen that in later time, so like scale factor equals to 1, they're very different. So it's much lower in lambda CDM because the pileup is a lot like slower, a lot like later. Okay, so we could see difference of using lambda. Now here comes the last part of the presentation, the in-body simulations. Then Demchenko et al. Also use simulations to compare with the model. So firstly, let's talk about how the simulation works. We use the box of 1 gigaparsec cube, and cosmology has like matter around 24%, dark energy around 76%, and we have the algorithm called spherical underdensity algorithm. That firstly, they count only the mass higher than 10 to the 12.8, and h minus 1 like solar mass. Count that is counted for calculating average density. So average density is said to be quite high. Then we find the local density minima and grow the sphere until the mean density reaches threshold. So grows it until the contrast reaches 0.2 of the average density. That means and then that point is the void radius, determines the void radius and its center. So by using massive halos, we could identify also the big voids, and spherical model approximation could work better with big voids because when the void is big, then the gravitational pull could be averaged out inside the void, and the pileup could go like later. And the initial conditions for a spherical model is like initial density profile and the total velocity profile that comes from peculiar velocity. Actually, this one is quite important, but we don't have the time to cover it here, so details are not mentioned here. So I'll only mention about the density contrast. Okay, let's see. So the solid line is from spherical model and dashed line is from in-body simulation. And the top one is for the void that has size like 40 over h megaparsec, and bottom panel is 20 over h megaparsec. So the bottom one is smaller void and the top one is larger voids. You can see that larger void appear more underdense and have fewer shell crossing. It doesn't have the peak like the smaller one. So the smaller voids experience, because smaller voids experience stronger differential gravity. We could see it like this, difference between gravitational acceleration. So it's like differential and times delta R, and the relative velocity of piling up is kind of like square root 2gh, like base classical equation. This one I just want to see the scaling of things. So since a smaller void has higher gradient of acceleration, is steeper, then larger delta G, and then larger velocity, so stronger pile up. That's why a smaller void has stronger pile up or peaks. But the peak is not does not correlate well with the model. You could see that the blue peaks are very different. That could be because of the simulation effects. The first one is miscentering. Like the small voids could move more easily than the large voids, so the center could move. But we fix the center at that point when we count or we measure the density. So there could be miscentering because the voids are moving. And non-sphericity, because smaller voids could deform more easily because it's not so big and the shape could change more. So it's not spherical anymore. We could not approximate it to be. Yes. So these effects are why smaller voids appear more inconsistent with the approximation with spherical model. Okay, in conclusion, spherical evolution model, we could use that to explain the void in our universe. By our universe, I mean using lambda CDM, and it provides accurate initial density, peculiar velocity. With provided initial density and peculiar velocity, we could produce the large void evolution that could precisely be predicted only for large voids. And the voids are promising probes for like dark energy or gravity, modified gravity stuff. But when we model it, we need to consider a lot of properties inside when we do the approximation. We have to account for velocities to avoid miscentering because center could move, and also the non-sphericity, and also like some observational systematics, like there could be some other matter around the void, like black holes, like or supernova. We have to consider that in real life. So we have to be very careful about our approximation. Okay, and that is all for my presentation. Hope you'll enjoy. Thank you very much. Thanks for listening. And this is the reference.